So this is example number 1 for failure theories for brittle materials. Let's consider the following case. It's very similar to the problems that we had in the past for ductile materials, but the difference is that now we are using a great cast iron material, and the ultimate tensile is given by 26, and the ultimate compressive is given by 27. So we know your ultimate tensile strength. This is KSI. You know your ultimate compressive strength, 97 KSI, and Italian strain fracture is 0.0002. This is less than 0.05. So definitely this is not ductile. This is acting like a brittle material. There's no plasticity zone in the problem. Okay, so when I do these type of problems, when you're doing these problems, the first thing you have to understand is what is exactly that you want to do. You are trying to find the factor of safety, and the factor of safety for these problems, but uh, we got the maximum normal stress theory. That basically I'm going to use either the factor of safety is either equal to sigma uh, sigma uh, tensile sigma 1, or it uses compressive over sigma 3, depending on the case that you're working with. The ductile column Moore theory says that this is equal to 1 over the factor is absolute value of sigma 1 ultimate in tensile minus 3 ultimate in compression. Okay, um, and then you have the modified. The modified has various cases, and we will just talk as we move along in the example. Okay, so let's work with the very first case. The first case that we have is the following. In this case, I have a state of stress. Always a good idea to write the state of stress so you can have a visual representation and understanding of what's going on in the problem. So this is all 0. So you know this is a state of stress because they have a 0 column, 0 0 row and 0 column. It's a diagonal matrix, stress tensor. So therefore, since it's diagonal, it is a principal state of stress. Okay, so I don't even need to run my code or anything because you immediately know your sigma 1 is equal to 30, your sigma 2 is equal to 30. But let's go ahead and run the code. And for this particular example, as it was the case before, we're going to assume that your design factor is equal to 1. If it was not equal to 1, remember you need to multiply all these values by that. Okay, so again, this is the failure theory, and you run the code, and this is inches, is in KSI. We're going to use a load factor of 1. This is stresses, we have stresses, that's what we have, is brittle material, and then the value was 26 and 97, 26 and 97. Your stress concentration factors, well, the stresses are given. Since the stresses are given, we can just take this equal to 1. The stresses all include any type of discontinuity that the problem has. As it was before, I'm going to apply this to the axial or bending. I can apply to both. So it was 30. So let's just put 30 there, 0 here. Put 30 here, and everything else was 0 in this problem. Okay. And yes, the loads, the factors are already applied. You let it go and you run. So Now that you're done, you can see that for, let's do the plot and understand what's happening in the plot. You can say your point is right here is outside all our boundaries of any of the cases, so you can immediately conclude that this is a failure point. This is a point that's not acceptable. Okay, so and then you can also see from here that your summary of design points and your factors of safety is all equal to 0.86. If you want to know more in detail, there's a file called brittle.txt. In this file, this goes into detail how you calculate everything. This is your state of stress. These are your principal stresses. The overall shear max, you really don't need this value for this particular case. Failure determined when this is less than 1. You do your checks. And you know, this is very interesting, right? This gives you 0. This gives you infinite. But that kind of makes sense because you are basically, the problem that you have in hand, your problem is completely in the is the locations 30 and everything else is 0. So you don't have no values in the S3 direction. So that is expected. So the maximum normal stress theory, then you use each one of these criterions, S1, S3, S1, S3, and then you can see in our case, when we had our case, all my cases were actually positive, right? So I'm working with a case like this, okay? I have double values positive, and then my S3, S2 will be 0. Okay, so that's the case number 1. So that's the case that we use, tensile. And SUT divided by this, that gives you 26 divided by 30. You can see the exceeds this value, so it's 0.86. And the modify more, basically either they're all positive, they're bounded, or they're all negative. Depending on the cases, this is the equation that you're going to use. So the equation that it's also using is the same in this case. And you can see that you kind of expect that. Why? Because in this region, all the 3 theories are the same, right? So you can expect I'm going to use exactly the same theory for my answers. Okay, to modify more criterion, this is very popularly used, but you have to watch out when it's less than 0. You have to set it to 0. That just says that you cannot use this method. You need to use a different method. And if it's 0, the one that I like to use is just assume that this is equal to this and move on. We will do an example, and you will see that that case will show up. So in this particular case, you just replace all the values, as you can see here, get all the values, and then that actually gives you what you're looking for. And then at the end of the day, you get this, you can scroll all the way down, you can find the summary of all your margins. Okay. Okay, so let's go with the next case scenario. In this particular case, it's the case of pure shear. And if we rewrite your state of stress, you see that everything is 0 except this value. This is symmetric. And I don't have any other stresses given in the problem. This is case of pure shear. Okay, so let's run our code and see what happens. And once again, choose failure theory main. You run your code, and that gives you 1 KSI. Assume this is 1 because everything is given. We have stresses. It's brittle material. The material is 26, is 27. Assume that all the factors are already applied to the problem. This is all zero. We don't have no normal stresses. We have only one. As it was before, we are only going to apply this to one of the cases. We're not going to apply both. We don't want to double dip. So let's say I take this vertical, I put 20, then I put the zero there. Remember, they're added up. So you cannot put 20 twice. Otherwise, it will be double dipping. Okay. Now we let it run. And we run the problem and let's see what happens. And now in this particular problem, now you see that you come to this point and you say, I barely passed this one, but I told you that column more, this is very conservative, so we don't use it. We use the modify more criterion, and it's way safe here. And you can, and that actually shows you in the results itself, right? You can see how your factor is actually 1.3. 1.3 for all the cases actually. That's because in this particular line, they all coalesce in the same point. If my load was somewhere here, then you have seen a difference. It's a case of pure shear, so you can expect a beautiful 45-degree angle here. The ratio of the paper doesn't allow you to see that, but this is 45-degree angle. And this point right here is the point of actually, the shear, the intersection of that particular location. So this is this particular example that this is, for example, sorry, this is for this example. Now, if we go move on to example number 3, let's see what happens. Again, you can run all these cases by yourself. I care a lot about the results of a final answer. So when I hit play again or run, this is ductile. I'm using 1. These are stresses. Is brittle material, 26, 97. This is 1, this is 1, this is 1. And this particular case, what I have is, the first case is minus 40. Then I can put 0 next. Minus 60, 0, and put 15 and 0 all the way rest of it. And yes, all the loads are applied. I let it run. And you can see that we are safe. And if I plot this, because it's positive, you expect this to be in this bound inside this region, and I'm actually located completely in this axis, okay, fully in this axis. So therefore, you can expect that that you will all get the same values for my margins of safety. So this dot right here is very important, right? It can be here, it can be, where is your dot at? That's your values. Those are the values that you're looking for. The very last case, the last case I want to do, the last 2 cases I would like to do is the minus 50, 50, 50. So I have 2 more cases. Let's run those cases. So what happens? Let's run this again. This is inches, KSI, 1, stresses. We're working with Brittle, 26, 97. This is 1, this is 1, this is 1. And this is all the cases minus 50, minus 50. So minus 50, minus 50, minus 50, and everything else is 0. Yes. So you run this case, let it run, and you can see that in this particular case, you actually end up being completely compressive. It's negative point. So in this location, 50-50, that's where you at, because all the stress you have, sigma 1, sigma 2, sigma 3, they have all the identical stress value. And this is the load line that you're working with. Okay, so this is a very interesting case, hydrostatic pressure, and it's very common, especially in the aerospace, in the aerospace industry. The other case is all positive, 25, 25, 25. Let's run that case as well. Let's see what happens. So move this up here, working in inches. Feel free to pause the video and download the file and run it with me. Okay, in addition to taking your notes on how the answers actually work. Okay, then this case was all 25, 0 here, 25, positive 25, and everything else was 0. This is 1. Okay. Remember, in order to run this, you need to close the file first. Otherwise, it gives you error. That's what happened. In this particular case, you're working in the case of is pure tension. Okay, and it's right here in this particular location. Everything is at one point. Okay, so those are the two extreme cases that I wanted to discuss with you here. And this concludes example number 1 for brittle material.